Hey everyone, welcome to the CS Education Zoo. This is our 9th show. Welcome to the new year, 2015. And to introduce you to this week's guest, here's Steve.
Hi everyone! Welcome again to the zoo. We are here this time with Colleen Lewis. And Will, can you put Colleen on so we can see her?
No.
No, you can't.
I gotta kick her off.
There we go. I'm still seeing you.
Are you?
You know what I look like. This will be fine. Roll with it. Roll with it.
Okay, here we go. Now I see Colleen. Oh, now I see Will. That's all right. I'll introduce Colleen, and afterwards there will be a quiz as to which of them is Colleen and which one is Will. So Colleen Lewis is a professor of computer science at Harvey Mudd College who specializes in computer science education. Colleen researches how people can succeed in computer science regardless of their background or their personal characteristics. And I don't use the word success here lightly. I love the fact that Colleen's research has this really positive viewpoint when you read it, and it often turns on the assumption that students have strengths that they bring to the table as they learn computer science, and that leads to some cool research, and it also actually makes reading her research a lot more fun than reading doom and gloom research. So I really love that aspect of what she's doing. Also, very near and dear to the zoo's heart, she curates csteachingtips.org, which is an NSF-sponsored project for disseminating effective computer science teaching practices. And I think I might start by asking you about the elephant in the room there. Colleen, is there something behind you?
Thank you for asking. There is. So I have this project, csteachingtips.org. We're NSF sponsored, like Steve said, and the idea is, well, here's really where it came about. Was in grad school, my advisor was Mike Clancy, who some folks in CS Ed will know, and I would go to him after TAing, and I'd be like, Mike, I figured it out. Like, I know why they're having this problem, and why my explanation wasn't working, and so I should explain it in this way. And for every one of those, he was like, oh yeah, of course. And I was like, you knew that, and you didn't tell me? And so part of it is just, like, experiencing this frustration with Mike Clancy not having poured everything that's in his head into my head, and trying to find people like Mike Clancy who are expert computer science teachers and put some of their ideas about the teaching and learning of computer science on the internet. So the basic idea is a new or experienced computer science teacher would say, hey, you know, I'm teaching arrays on Monday. Maybe I've taught it never. Maybe I've taught it 100 times. What are good ways of teaching about arrays, and where will my students have trouble? So it's providing insights into both sort of directions of what are the pitfalls to avoid, and how do you make this accessible to your students.
Oh, sorry.
I was just going to say we've got a ton of tips. Right now we've got 350 and growing.
Awesome. So this was one of the questions that I had, which is kind of where I should go into CS Teaching Tips. So I went and I explored a little bit, and there was neat stuff on there. And weirdly enough, I wasn't thinking about my own course. But I guess what you're saying is I should be going in there and saying, well, you know, I'm going to talk about greedy algorithms on Wednesday, and I haven't talked greedy algorithms in a while. I should take a look at that.
Yeah, I think that's certainly a viable way. Right now, our search functionality is a little bit broken, but that any of the bugs, or we might call them features on the websites, I think are all temporary. And so I think in the long run, it'll be a good place to say, I'm teaching this. Let me dig in and get some insights in how to teach that. I find it as an educator terribly addicting just to read through them. Like, I'll click on the related tips and find myself kind of engrossed in those tips. I've been amazed with, you know, one of the problems people told us was, you know, after you've interviewed 10 people or so, you're not going to get new tips. But that's not what I'm seeing at all. We get some of the same tips, but you know, when you're teaching inheritance, talk about cars and different types of vehicles. Okay, we've gotten that one a few times, but for a lot of the tips, there's really a lot of variety. So particularly thinking, you know, 20 years into my career, rejuvenating my ways of teaching, trying out new approaches. I think it will have functionality to search and then test in my classroom.
That makes a lot of sense. Oh, so can you share a favorite teaching tip with us from Teaching Tips?
I certainly can. So
okay.
Maybe this is selfish, but I thought maybe it makes sense to share one of my own tips, and in particular, I thought it could be animal themed. So a lot of people have given us the tips that when they're teaching inheritance in Java, they draw stack and heap diagrams and things like that. Something I think is really helpful is making that concrete. So it's helpful to me to be able to refer to a specific object. So this is my childhood, it's actually a puppet, my childhood puppet that I can bring to class. And it has a label that says, I am a dog. And I use the head first Java strategy of referring to Java references as remote controls. Let me get my dog. So I have a dog remote control, which is just a cereal box covered in paper. And I can then point to my dog. And then if I can keep everything balanced, I also have, maybe my parent class is an animal. And so I have my parent class remote control, which also points to my dog. And so it's, I think, really helpful to be able to talk through the scenarios where, what if two things are pointing to this same dog, and one of them calls a method that modifies this dog? Then, I think it's sort of intuitive using the remote paradigm or the remote metaphor from Head First Java to be able to think about what happens to this dog. And then I have a number of other animals that make appearances in my. I also, something I haven't figured out a good strategy for is, when I'm making an animal, like my animal object, if I don't have it as an abstract class, as I have it just as a regular class, what should represent an animal? And right now, what I use is pumpkins, but and maybe I just need to make it an abstract class so I don't have to have a physical instantiation of it, but I haven't figured that one out. Do you want to see another tip?
Yes, I would like to. That was great. I really like the remote control idea. I didn't see that in Head First Java. I flipped through it, but I didn't see that metaphor. That's great.
The reference, the variable is a cup that can hold a remote control. And so then when you pass around, cups can hold numbers like primitives, and then when you pass those around, they get a copy of what's inside the cup. So it might be the number 7, or it might be a remote control. So you get copies of remote controls. Okay, I have one more.
Don't hurt yourself.
Yeah. Okay. So the thing I think is really interesting in teaching introductory computer science is students who are at the state where they say, I know what I want to do, but I can't write code to do it. And I think trying to bridge that gap is like a fun challenge. So I think, so one of the strategies I've used is here I've got Dixie cups for teaching about arrays. And I think a lot of people do that. When we've been talking to people, they've said that they use Dixie cups, or egg cartons, because you can do a 2x2 egg carton, to represent arrays, to capture the idea that you can hold things inside of it. But I like to use it for say I have an array, and here I have 6 elements, and I want to find the maximum value. If we have students just look at an array that has 6 elements in it, they just can see what the array, the max value is, and they don't even have to think about it. So what I do is I take Dixie cups, and I make class sets so that students can do this in lab. I take Dixie cups and write numbers on the bottom. And it's important that they're on the bottom because here, from your vantage point, whatever, you can't see where there are numbers. But for mine, I can see into the cup, but I can't see any of the numbers. So if I'm going to go through and figure out what the maximum number is, I have to actually flip up the cups and make the array references explicit. And so another thing and then once you have these cups in lab, you're like, well, what else can I use the cups for? And And something that I found startling is that students find heap operations. Maybe I'm bad at explaining them, but when I explain heap operations, they're like, oh my goodness, this is the most confusing thing that's ever happened. But when I just had them use the cups and draw out, either in tape on the floor or on poster board, a maximally balanced binary tree, and have them manipulate the cups, oh, well, I'm swapping these two, let me pick these two up and swap them. They're like, oh, this is like the easiest thing ever. And so I think with, in elementary school classrooms and stuff, there's a lot of these like manipulatives of like the little blocks and things. And I think one seems to be the magic. I haven't figured out a better way to explain heaps than just to have people touch the cups once, and then it seems fine. And in particular, the manipulatives to bridge the gap between I know how to do it, but I can't write code for it. I think this can be a really helpful intermediate step.
Yeah, and I can see that finding that way to hide the information that's so obvious when you draw something on the board makes a big difference. I have that trouble with tree data structures. In my data structures class, you draw out the tree and you're like, where is this element of the tree? Well, you just look at the board and you see where the element of the tree is. But
right? Yeah, and I recently bought these little like little restaurant numbers.
Mm-hmm.
And these are helpful for the like big classroom demos because sometimes I'm teaching 100 people in a class or something. But it doesn't have the same affordance. Sort of for in the lab use, I like something where the data is hidden.
Yeah.
And certainly playing cards work in the same way. I just think they're not as satisfying to pick up. And maybe that's a silly reason to use Dixie cups, but yeah.
I like it.
Yeah. I have one more if you want one more right now.
Yeah, go for it. This is great.
So in one of our homework assignments, we use a linked list node that represents the empty list or a terminator node, and it's just, we call it the empty list node. And I've used an empty plastic bag. Usually it's just like random trash that I have to have in my backpack. And this was the random trash I found in my office just now. But using this to be like, look, there's only going to be one of these empty trash bags, and I'm going to have multiple remote controls pointing to it. Again, to make that embodiment concrete.
Mm-hmm.
Okay.
All right.
Those are my teaching tips.
I like them. That's great.
Yeah. So we have a lot of stuff like that. Over the summer, we're going to be working on providing more videos so that you like the CS Unplugged, where you can go there and see videos of it being enacted, so that we're trying to add more visuals and videos so that you can see some of the tips enacted and really get a sense of how it would work in your classroom.
Okay. So when I was thinking about you talking about the teaching tips, I was imagining you'd show us some teaching tips, which is great, you did, and they were fabulous. And then the other thing that came to mind was I used the site a little bit, and I was imagining myself using the site, and I was kind of wondering how you feel about this slightly weird question, so feel free to say that's a meaningless question, but how important are the tips themselves versus getting people to go and look at tips and play with teaching ideas?
Oh, I think that's an important piece. So I think it's a really sort of deep philosophical question of like, how does teaching practice develop? And 1 part new ideas, 4 parts reflection. Do you know what I mean? That I think.
I didn't expect you to give an exact ratio. That's awesome.
Yeah. I might pretend I didn't say that later on, but I think so. I think there's nothing better than having a peer or even a student that you can talk to and reflect after your teaching about how it went and what could have been improved and what went too quickly and what went too slowly and what metaphors stuck and what metaphors broke down and understanding and really digging deeply into the experience for the student in that classroom. But sometimes, I'm gonna go to in gathering the CS teaching tips, I've gotten tips that none of my colleagues, even when I'm talking to them about my teaching practice, have shared with me and have been helpful. And so I think, I think it's been really, really valuable in that. So I think that this is one way in which you can improve your teaching practice.
Okay. Will, my next question is going to be on a different topic probably, unless you've got a follow-up. You want to dive in?
Sure. I've got a question. So the teaching tips you showed us were very sort of physically based, right? And I assume sort of the intention is to take some of the topics that are much more, abstract and make them more concrete. Do you have teaching tips that you like that maybe sort of either go the other way or don't have physical manifestations, or what are some other teaching tips that maybe have a different flavor?
Yeah, so I think the physical teaching tips are the most interesting to show in video, but might not be the most important ones. So I think some of the ones that relate to student misconceptions can be particularly helpful. So one of the teaching tips, and this segues into some of my Scratch work. So I've been working since about 2007, teaching around 6th graders, 7th graders Scratch, just in odd places here and there. And one of the things I found is that, I had one experience where I was at a Girl Scout career fair, and I was showing off Scratch, and I would drag a block out that said move 10 steps, and I'd be like, what do you think will happen when I click on it? And they're like, it'll move, a little. And I was like, yeah, and then what if I click turn right 15 degrees? And they're like, oh, we also think it'll turn. No one's surprised. And then I would stick them together, and I'd say, what do you think it would do if I double-clicked on it now? And they're like, it would do them at the same time. And I was like, oh, no, not at all. It just does them one after the other.
That's such a reasonable thing to think, though, right? Why doesn't it do that?
And, and it was early in my grad school days, and just an organic experience, but I probably showed 100 girls ages, maybe 3rd through 6th grade Scratch, and they all had that same assumption. And the big problem with it was that when you double-clicked on it, you couldn't tell that it didn't happen at the same time. I also had a...
really fascinating.
Right, because it just happens too quickly. I also, in grad school, collected data with students using Logo, and one of the cases that I analyzed but only turned into a class paper was a student who didn't realize that things happen sequentially. And I have audio and video of me trying to coach her through understanding how the Logo program is working. And, a month after that exchange, watching the video, it became clear that she didn't understand that it was sequential. And it was just a disaster. Can you imagine trying to debug programs of any length if you thought that it all happened at once? And in particular, the move and turn is really problematic in Scratch or other Logo-based things, because as humans, when we turn, we very, very rarely turn without moving. And so this idea that we're going to turn and that's not going to draw us, we're not going to trace a circle with our body, that we're just turning our orientation, is a hard idea. So I think that captures another a misconception teaching tip. And then additionally, we have a sort of positively framed teaching tip, which is, if you're teaching Scratch or things where you want students to understand that program execution is sequential, start with sounds. This isn't universally accessible. If you have deaf students, it's not going to have the same effect. You need to pick a set of blocks to use that will make the order of execution explicit. Because, and so I have a Scratch course on edX that's starting in a few weeks for middle school kids. And in there, what I do is the first programs that students write, is working with sounds and ordering sounds. Because if you double click on 2 sounds and it happens one after the other, it's not mysterious at all.
That's actually fascinating, and I think that's also a really deep observation. Several ways based on what people understand or what they imagine is going to happen. The other thing is there's been a lot of complaints that in a world that now where we have all these parallel processors and things like that teaching people sequentially is actually not necessarily the right way to teach them programming. That actually we should be teaching them how to think parallelly, and then have sequential be a special case. And there are programming languages like Parallel Haskell that are like that. And there's even a version of Logo, I think it's Star Logo, that's massively parallel, and you draw a circle by taking the turtle, randomly selecting which angle and moving it one, right? And there's a million turtles, and it kind of draws a circle, stuff like that. So that's really interesting. And the other thing I think of when I think of this is, the original version of Logo had an actual robot turtle, right? And then there are these scribbler robots and things like that. And I wonder if seeing the physical action of a robot drawing on a piece of paper makes it a little more concrete in terms of the sequentiality of those operations. I'm not sure. Maybe we may have lost something by going virtual.
Yeah, and one of the things I do when I teach Scratch with students is I take sidewalk chalk and I make shapes. So I make a square, a triangle, and a circle. In class, I have the students give me instructions for how I can draw a square. And then they go out, and each pair of students has their own set of shapes. They've already heard how to do the square, so they do the square another time. Then they wrestle through the triangle, realizing that they don't just turn 60 degrees at each corner. And then for sort of, early middle school, late elementary school students, it's a crazy, interesting intellectual task to conceptualize how you take moves and turns and make a circle. And so, but it's so I'm really into it for that type of work. I'm really into Pappert's idea of becoming the turtle, and playing turtle is what he calls it. And so I have students, before they do any of the shape drawing in Scratch, play turtle using traced out shapes on the ground.
Like a first-person turtle game? Mm-hmm. Are there such things? Has anyone made a first-person turtle game? It seems like an obvious thing to do, but I've never seen anything like that.
Doom Logo.
Doom Logo, exactly, right? Doom Logo, I mean, that would be a way to play turtle, first-person turtle.
Yeah. You still want some of the perspective, though, so it's almost, I think the experience of getting to be the turtle is helpful, but also work with your partner and give your partner instructions and see how your instructions are causing them to move around a physical space, because we need students, when they're doing drawing in Scratch or Logo, to think about that as a 2D physical space. So I also encourage students, I have, when I teach middle school students, I have debugging tips on the board for them of like, you're stuck on something, let's try one of these debugging tips, and one of them is to play turtle and have one of the pair programmers stand up and be the turtle in the classroom.
Cool, thank you. All right, Steve, you have another topic?
Sure. Well, Colleen, you just mentioned that you're putting a MOOC up on edX for learning Scratch. Can you tell us a little bit about that MOOC?
Oh yeah. So I've been teaching this like 6th graders, and I've been teaching a summer program starting in 2008, and it's a 36-hour program, and I've been doing a bunch of research in that context. And one summer we had ethnographic researchers sitting in the class. So these were students that we hired who had been trained to sit behind some of our focal students and take notes on what they were doing and how they were engaging with their partner and their body language and stuff like that. So they were taking notes during our class. And then the painful process the next month or year, as we were reading through those field notes, they're called, realizing these students were not listening to us when we were lecturing, not even like a little bit, not even our best students were listening even a little when we were talking. Yeah, and so some of it was the setup of the lab space was really problematic, that it was rows of computers, and so if I was standing at the front, I couldn't see everyone because there were these big, beautiful monitors in front of their faces. And also just the pacing of it was difficult, so I needed to provide the the activities that I structured in the class were self-paced, and so that meant that I had to provide a lot of sort of background introductory material before they started the day, which led to sort of 20 to 30 minutes of lecture, which were essentially wasted. So I realized this by looking at these field notes. It was a little depressing. And then next summer what I did is I made videos that would be interspersed. So any of the lecture content that I had given the last 3 or 4 years, I turned into 1 to 5 minute videos. So I'd explain a topic, they do something. I might explain the solution to that previous problem so that they're still going through self-paced, but now have sort of just-in-time teaching embedded within the curriculum. And then in a face-to-face context, I use these videos. Students often still were not paying attention to the video. They'd like put their headphones on and then be looking around. But it was a little easier because I wasn't having to focus on clearly explaining something and doing classroom management. When they were watching these videos of me, I could just be doing classroom management. So it was really, really helpful in my own teaching practice. So the idea is that teachers could use this MOOC in their classroom. I think, if you think about like, oh, you have this MOOC online, who's going to take it? People who are the children of computer scientists. That might be like the largest demographic of students who take the course independently on edX. Okay, that's not particularly compelling to me as a target audience. You know what I mean? That I really am passionate about making computer science more accessible, and those students probably already have pretty reasonable access to computer science. But I think there is great potential in this MOOC being used in classrooms. I've been distributing my the curriculum materials that I've used. I've been distributing them to folks around the world for years, and so just in the Bay Area, I knew of 10 people who were using my Scratch lessons in their classroom. Just another instantiation of my early MOOC, which was on Moodle. And so now I think having it on edX will make it easier for more people to use this content in their classrooms. So that's my real hope for it, is that teachers can try the course themselves and then use it in their classroom. We'll see.
So I like that, and thinking about how to use the videos. That was one of the things when I was first looking at your videos before I knew you were starting an edX course. I was looking at the videos and thinking how you use them in a classroom. So I've been doing just-in-time teaching in some of my classes for a while, and this was Novak, and some other people did just-in-time teaching a while ago. But regardless, my one-sentence summary of it has always been: you tell students to read the textbook and you mean it. Whereas I typically, in the past, I told students readings in the book, but half the time I hadn't even read the book. It was a new book that was different from one that I'd used when I put together my course materials, and it's probably the right stuff in there. So I'm wondering, like, for just-in-time teaching, the idea is basically tell them to read the textbook, give them some sort of quiz so that you know that they'll read the textbook, and then you can build on that in class, maybe getting some of their misconceptions. Would you do the same sort of things with videos, or do you feel like the best use is kind of different?
I think you can, another way I've heard just-in-time teaching is a little bit broader, which you can think of it as in a tutoring context, where once the student needs a new skill, you introduce the new skill.
Mm-hmm.
And so I think that this has that general frame. Like, I wasn't having my summer students, I wasn't having them read before class. I was having them do homework that included case studies, but I was, in general, just presenting information right before they needed to use that information, and then reviewing that information, and then presenting new information. So it had so I was trying to sandwich their practice into an introduction and reinforcement of those ideas.
Mm-hmm.
And it's a little tricky to use sound in public school classrooms, but headphone splitters tend to be kind of expensive. But what I figured out this last year is I bought a huge box of really cheap headphones, 40 cents a piece. And I just took them and I broke the middle part right there,
Mm-hmm.
And then they become earbuds, so each kid gets one earbud. And then it's not going, like, in their ear. That grosses me out. I don't know if it's actually, like, a concern, but it grosses me out.
Yeah. Based on my child of a computer scientist, it seems like lice is probably the big concern, but fortunately we don't have to discuss lice.
Yeah. So break cheap headphones, break them, and put them. Yeah, that's what's worked for me.
That's a cool teaching tip right there.
Yeah. I meant to take photos, yeah, but.
So, Will's asked about this a little bit already. I want to follow up on it. I love Scratch and the other block-based languages as an idea for interest to CS, and my child of a computer scientist right now is using these new robots called Dot and Dash that have a Blockly style language, and she loves it and she's so excited. And I'm wondering about transfer. And whether there's, I guess in some sense what I'm specifically wondering about is not transfer for my daughter or for my students if I teach them Scratch, more like transfer for my colleagues who say, no, we can't use Scratch because they're never going to learn anything. How do you convince someone that they'll learn something in Scratch, and in the process hopefully convince yourself that they're really going to be able to transfer to whatever language 2 is?
Yeah, so I've done a lot of work with Scratch. I'm really happy with Scratch. I helped design my 6th grade computer science content became the first 4 weeks of the Berkeley Beauty and Joy of Computing course, one of the new computer science principles courses. And so I helped launch that course with Dan Garcia and Brian Harvey at Berkeley to have a Scratch-based, even though it's Snap, Scratch-based programming language in the intro course at a college level. But I'm still not convinced, and I want to add another concern to the list of concerns. So one is transferability. What are they learning in Scratch that they're going to be able to transfer to other contexts? And the second one for me is confidence, because Scratch doesn't look like a programming language, it looks like a game. And that's both advantageous in terms of drawing students in, but I worry about the extent to which that doesn't accurately build efficacy and belief in in students' ability that they can succeed in computer science. And so I've been doing some studies around this. So in 2009, I have a 2010 SIGC paper where I had 6th grade students program in Scratch and 6th grade students program in Logo. And they did the same exact task, so they accomplished the same goals, but just using either language. And the students who learned Logo did a lot worse on my assessment. So they just didn't have as firm of an understanding of conditionals and loops as the students in Scratch did. So for a population that doesn't feel comfortable typing, it was like Scratch was a clear winner in terms of my computer science learning goals for them of learning about conditionals and loops. But the students who learned Logo were much more confident in their ability to program. And it was statistically significant that they were more confident. They, am I good at programming? And the Logo students thought they were. And so this has been kind of an ongoing thing that I've been investigating in my research. So I have a paper. What do they think Scratch is programming? What even do they think Scratch is programming? So one of my studies suggests that they think that the picture from the Matrix where there's those green numbers streaming, they think that's programming. A lot of them rated that as definitely programming in a little a picture sorting task because they said it looks complicated. And so I think it's really interesting working with a population, particularly younger students who don't have a sense of what programming is, to say, Scratch is programming, and here's what you're learning. And I tell them that 100 times in my 6th grade summer camp, but I think, still don't believe me. And so I think, the thing I've been doing in my Scratch course to try and address this is they do Scratch for 25 hours, and then I give them a sheet that translates everything they've done in Scratch into a version of Logo. Mm-hmm. And I make them redo almost all of the assignments that they had just done in Scratch, but typing it in Logo. So they're like, oh yeah, well, I can just look at my Scratch code and then I just type it in. It's like trivial, the change. And I want them to see how changing to a typed language, like typed language, is a trivial difference between Scratch. But I think I haven't convinced them of that because it looks like a game. This past summer, I did a new study where you're going to want me to have the results from this study, and I don't have the results yet, which is 2 classes. One of them started with learning JavaScript using Codecademy, and then as a baseline for, hey, if you take kids who have no programming experience and you teach them, let me plug in. Sorry. If you take kids with no programming experience and you teach them JavaScript using Codecademy, how far do they get? How much do they learn about JavaScript? Then I have another group of kids who programmed in Scratch for about 25 hours and then did that same JavaScript tutorial on Codecademy to see, do they make more progress? Do they understand the content at a deeper level? To see to the extent to which they're transferring those ideas that they've developed from Scratch into a language that isn't a carbon copy to Logo. Or, you know, it isn't a one-to-one translation, but they're having to transfer those ideas into if statements that look a little different and loops that look a little different and function calls that look a little different. So I'm going to push to get that paper out by ICER's deadline, but we'll see.
Well, maybe you can come back and tell us about the results on that one when you've got them.
Yeah. But I think it's a tricky problem. I think we don't have the answer we need in terms of how to convince students that this really is programming and how to help students engage with these ideas in ways that they're going to be able to extend outside of the Scratch programming context. We're not there yet, but I think it's the best we've got.
Well, you've certainly given me something new to worry about with my daughter. That's good. Parents need things to worry about. How will I convince her she's a programmer?
Yeah. Yeah, I think you can play your hand kind of slow, though, as a parent. You know, that like, oh, it's just this fun game. What do you mean, programming? No, it's unrelated. And later,
it's a long game. I agree. Yeah. I've got more than 6 weeks.
Yeah.
The long con of parenting.
Yeah, yeah. Yeah, but I feel like I only have these 36 instructional hours to convince people that they're really programming. So that's something I'm really worried about in the edX course is, you know, convincing potential teachers of this content in a classroom setting and convincing students of this content. Like, you're doing real computer science. There's more interesting stuff in Scratch to do, but I'm teaching you the computer science. Like, you know, so, and that's, like, how I picked the course content was to reinforce iteration. Iteration is one of the big concepts that I pick up on in that edX course. So they're writing loops that iterate with a variable in 6 different modalities. And another thing I'm picking up on is trying to do iterative development. So if we want to get from here to here, let's break that up into 4 different pieces and work towards that goal. And you know, you're not going to get that in the typical Scratch course, but you are going to get that in a Scratch course designed by a computer science professor. Like, oh, let's teach you some cool stuff in Scratch, but also let's embed as much computer science as we can.
All right. So you've actually just made a bunch of connections to previous zoos that I was thinking about, but I was thinking ahead to one connection that might come up. Which is live coding. We've had a bunch of people talk about live coding. And I was watching some of your Scratch videos, and I'm pretty sure you didn't live code them. You scripted them out, right?
Oh, no. Those videos are all essentially one take. I mean,
one take, but you plan things out, right? All those videos is lectures I would have given during class. Sure.
But as I'm talking, I'm dragging the blocks out.
totally understood. I just mean you plan ahead what's going to happen, and if you're gonna do this and say, oh, it didn't make a square, you plan ahead for it not to make a square, and then.
Oh yeah, but I actually, that teaching tip of just like making mistakes on the fly, I think has limited utility as I continue in my career, because like the task, I just don't make as many mistakes. Some of these like little lecture-sized examples, like you have to build in mistakes after you've taught it 6 times.
Mm-hmm. Because it's all in your fingers already.
Yeah.
Well, so what I wanted to ask was, there is that difference then between live coding and a video that looks live. It looks like live coding, but it is pre-planned, and you get a lot of time to think about, is this the take I want? Do I want to do a different take? Can you talk a little bit about how you get some of the advantages of live coding into a video, and how you maybe avoid some of the disadvantages?
Yeah, I wouldn't make videos for a class I hadn't taught before. And so the really nice thing about one of the advantages of getting to plan these is any mistakes that I've seen in my years of teaching this exact lesson, I can integrate into one of the videos so that I get to highlight those mistakes. And I think, it doesn't. Some of the students that were in class with me this last summer and listening to the videos of me all day long, and with the intro screen that says Programming in Scratch with Colleen Lewis, didn't know I was the voice on the video. We were like 30 hours in, and a kid was like, wait, that's you? And I was just like, how? Okay, whatever. But,
it's like I went back and watched Mr. Rogers as an adult, and I realized he was making the voices of like the cat and stuff. It's like, I'm Mr. Rogers. That just blew my mind. I never made that connection.
Yeah.
Meow 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 meow.
Yeah. So I think part of the beauty of live coding, and someone I've seen do live coding, Phil Conrad at UCSB, does awesome live coding. Is this personal connection with the students? Do you know what I mean? We're all in this together. I'm going to get ideas from students, and that's going to shape what code I write. That sort of relationship building part of live coding, the expectation setting that even experts make mistakes, I think is you lose in the video. One, because my personness is more invisible because you don't see my face in these videos. And, these people on the MOOC, they're not going to know me. And even my students who knew me well from the class didn't realize that I was the voice in the video.
Colleen Lewis, played by Colleen Lewis. Oh. Okay, I mean that's very good. That's what I love about teaching students is bringing, it's not me teaching, it's everybody getting together and learning.
Yeah.
So, I mean, I guess what you're saying, based on how you're talking about using the videos, then is use the videos to have that just-in-time chunk of something for students to learn, and then have someone there, some other facilitator, to do that community formation part.
Yeah. Yeah, so my best stab at that is in the intro video, like, hey, take my course that I made. I encourage people to try and find a friend to take it with so that they are doing pair programming. And so I'm going to add videos and reminders throughout to say, like, find a friend, etc., so that the MOOC experience isn't reinforcing the idea that programming is a solitary task. I mean, part of why I use, like, these puppets, is this was my childhood toy, and I think any opportunity I have in my classroom to communicate to students that computer scientists are people, I jump on. So like any algorithm that we learn that is associated with a computer scientist's name, I find some plausibly true facts about them on the internet about their hobbies. Do they like white wine or mountain biking, or I mean, I have a low threshold for what I might repeat about their hobbies in class, but I think it's really important to like communicate that these are people, you know?
Yeah.
And so these, you know, a lot of my props just are like, you know, this little guy is a stuffed animal I got while I worked at Leapfrog making educational games. And so if I need to bring this little guy to class, I'll tell a story about my experience working at Leapfrog. I think that my students just think that I like get distracted and tell them random stories, but I try and remind them that like, oh, computer scientists are people, like, you know, and I like want to make my humanness and my quirkiness present in the classroom so that you can't just get lost behind the like, oh, she's just a talking head who's a computer scientist who knows everything, etc.
You're not even a talking head. You're just a talking voice.
Yeah, certainly in the videos. Yeah. I move around a lot in my lecture, though, so I might be like more. I might look more like a talking aerobics instructor while I lecture.
Okay, I've got a question, Steve.
Go for it.
Yeah. So a question I have. You know, because I've read a lot of the writings of Peppard and Alan Kay and all these folks who are, you know, a lot of the things like, you know, Squeak and Scratch and so forth are obviously heavily inspired by their ideas. And one thing Alan Kay always talks about is, you know, computer literacy and a new type of literacy that's, I think maybe the best way he ever said it is that when he went to grad school, he knew nothing. He only knew how to program. And that really, you know, to him, these things are a way to try to understand big ideas and to run simulations or things like, you know, try to understand like the great intellectual ideas of the world. And that the programming stuff, you know, there are obviously very interesting ideas in like computer science, like undecidability and things like that. But that really, the real effort should be trying to get people to understand great ideas. And I was just wondering what you think about that, or you know, if that is at all involved in your philosophy, and what sort of ideas, if any, are you trying to get towards, or would you like students to get towards, you know, with this material?
Yeah, you know, one of my advisors is Andy DeSessa, and he's a physicist turned educational researcher, and so this was at Berkeley, and he has a book that talks about computational thinking. I think from 2000, so before the Jeanette Wing computational thinking CT buzz started. And I really buy into his model of it, which is, you know, before we had algebra, our expressive power in science and engineering was limited. And so, you know, we had language and words that we could use to express it, but none were as powerful as algebra. And algebra represented this like monumental leap forward in terms of how we could express scientific ideas. And I think and then DeSessa continues that programming offers that additional bump in our ability to communicate scientific ideas and make things that were difficult to express in algebra intuitive and easy to express. And so for me, the new literacy is that, you know, if one of my coworker, Melissa O'Neill, tells students on our Harvey Mudd tours, you know, like here at Harvey Mudd, computer science is required because if you're going to be a scientist or engineer, you need to know you need to have basic computer literacy with computer science and programming. Just like, you know, 100 years ago, to do science or engineering, you needed to learn math. And so I think of it as a node along this trajectory from like language and written language and algebra and programming as a way of expressing ideas. I think that's a little different than the question you asked, which is, you know, what are these beautiful gems that everybody should know about? Maybe.
Yeah, I mean, I think that's a really good answer. You know, and I've never completely understood what Kay meant, but I think, you know, Kay and some of these other people have this idea that, you'll learn computer science or programming so you can learn like the theory of relativity, or you'll learn like some really great conceptual idea, or you'll learn about DNA, or something like that. That this is basically an enabling technology to make other really fundamental ideas that we know about in the 21st century, really great ideas, accessible to people in ways that they aren't just from a textbook or something like that.
Yeah.
But I totally agree with what you're saying about sort of enabling different ways, new notation and expressiveness also.
And I think computation can make things accessible in a different way. So my coworkers Ron Liebeskin and Dawson Elliott Bush have computation for biologists or something like that, where they use all biology-themed problems to do introductory computer science. And it's both, and I know that I'm biased like as a computer science professor, but it makes me both more interested in those computer science problems and these like small little toy problems that we do in introductory computer science, and makes me more interested in the biology that backs it up. And so I think that this intersection of computing and other domains, I think computer science can motivate a lot of interest in those other domains and be a really powerful tool for scientists and non-scientists in their respective domains.
Yeah, that Harvey Mudd course looks really awesome and very innovative. Yeah. Very neat.
The problems seem really cool. I mean, just like, he'll tell us about them, like, just because they're cool enough to tell us about, like, oh, we're just chatting, and he'll share one that he's teaching in class that week. It's fun.
So Will, we went a while there on those first questions, which were great, but I have at least one more question I'd like to ask. Do we have time before shoutouts to ask one more?
I think we got one more question in shoutouts.
All right. So this is a regular one, Colleen. I just want to know, what's something you think every computer scientist should read, learn, do, play with? It can be a book, but it can be anything else too.
It would just be too cheesy to say csteachingtips.org, right?
Okay. So given that it's been above your head the entire time, I'm going to say it has to be something other than csteachingtips.org.
I mean, for me as a computer scientist, where a lot of times I'm not getting to write code as much anymore, is like getting to try new things that that are fun. Do you know what I mean? Like to get to continue making things that you want to make. I'm not so committed. I'm not a die-hard Scratch person. It's what I choose to use in my classroom, but it's not the end-all be-all. Yeah, maybe that doesn't totally answer your question, which was great because then it's a short answer.
No, I think it does answer my question. I mean, you're saying keep your hands in the making, right?
Yeah. Keep making things you think would be fun to make and fun to have.
Can you give an example of that? Like what's something recently that you thought, hey, this would be really fun to play with, and just kind of experimented with it or explored it or learned some new technology or whatever it was?
Yeah, so something I'm going to be doing with my students this semester is making dynamic visualizations of state and national test data. So, sixth graders in California take the CST or other sort of state or national educational tests or standardized tests. And I think that as a computer scientist, I can offer windows into that data set, those data sets that other folks that without a computer science background you couldn't. And so we're going to be learning a bunch of JavaScript and D3 and making a bunch of visualizations for both AP CS test taking data and California state test data to see how cool the visualizations we can make and see what insights we can provide to education policymakers.
There we go. Good, Will?
Yeah.
Will is satisfied. All right. So we should probably do shout-outs at this point. If there's anybody that you want to thank, anybody that you want to point us to, if there's maybe a URL or a Twitter address that isn't posted above your head that you'd like to refer us to, just let us know now.
Yeah, I'd like to thank the NSF for giving me some money to do this. I think it will dramatically change my teaching practice, and I hope to have the opportunity to change other people's teaching practice, even in small ways, through the csteachingtips.org or Twitter @csteachingtips.
So let me ask you to follow up on that shout out then. What if somebody else wants to do something awesome like CS Teaching Tips? Which NSF grant program should they be turning to? Where did you get your NSF grant?
Oh, from C21 is where we got our money. Yeah.
Oh, all right. And that's your shout out for the moment?
I think that's my shout out for the moment. Yay, Harvey Mudd.
Excellent. We'll put Harvey Mudd right there in the shout outs then. Awesome. All right. Thank you so much, Colleen. This was great.
This was a lot of fun. Thanks so much for having me on.
Yeah, thank you very much. And thank you for your childhood dog for making an appearance also.
Yeah. Wrinkles.
I'm super. Oh, what's the name?
Wrinkles.
Wrinkles. Okay, we'll have a shout out for Wrinkles the dog too. Wrinkles
Perfect.
The dog.
Does Wrinkles have a Twitter account or
no, not at the moment.
Why not?
Yeah, I know. Really, it's careless of me.
Is at I am a dog taken already? Or?
I'll check after this.
Excellent. All right, so yeah, thank you very much. That's a wrap up for episode 9, and we don't have our upcoming speakers scheduled at the moment. We've got a few people that we're in communications with, but if you out there would like to be on our show, drop us a line. Where should they drop us a line, Will?
I don't know. Email, Twitter. They can go to the CS Education Zoo website.
There you go.
And yeah, we got all the ways to contact us and so forth. So.
Excellent. So just search for CS Education Zoo. We are out there. And we'll see you next time.
All right. Bye.
Bye.